I learned that the worst wine in a wedding is left for the last hour of the wedding. So this is the worst wine of this wedding. But I'll try to make it as good as I can. So let's talk about spectral properties of graph neural networks. Let me begin by introducing graph convolutional filters and neural networks, which I think typically we make them more difficult than they actually are. The idea of a graph convolutional filter is that you are going to process your information with a polynomial on a matrix representation of the graph. Okay, you can think of the adjacency, Laplacian, normalized adjacencies here. And why do I mean by a polynomial? Well, because the idea of a graph neural network is to process information locally, right? So the first thing you're going to do is you're going to get your own data. Look at node 1 here, node 2, but this is going on for all nodes in the graph, and you're going to multiply that by some scalar coefficient. You then get the data of your one-hop neighbors, you multiply that by a different coefficient, and that is contained on this s to the power of 1, s to the power of 2 brings your 2-hop neighbors, s to the power of 3, your 3-hop neighbors. You keep repeating this for whatever number of steps you want, infinity just for reference, and that's a graph convolutional filter. This graph convolutional filter, you can represent it with this structure, which I hope is familiar to a lot of you. And the idea here is that you begin with your data. Your data starts to diffuse through the graph through recursive application of the Laplacian in this particular example. You sum all of these different diffuse versions, each of them is scaled by a different quantity, or if you wish, you sum scaled versions of the components of the diffusion sequence, and that's, again, an equivalent definition of your graph convolution. The thing is that, well, we have this graph convolution. You want to build a graph neural network out of that. This is what you do. You compose your graph convolutions with pointwise nonlinearities, okay? And that we do, by the way, because that's kind of like the standard definition of a neural network. It's a linear map followed by a pointwise nonlinearity. In this particular case, the linear map is a graph convolution. Something that is very important to notice here is the following. So the input to this architecture is a graph signal. The output is another graph signal, and the graph here S is given as a parameter. Okay, so that's something that I have found helps to understand what is it that a graph neural network is doing. It's not processing the graph, although indirectly, of course, it is. It's processing information that is supported on the graph. Okay, now the thing is this, right? So when I introduced this diagram, I said that this should be familiar to some of you. And the reason is that, maybe you have never seen graph neural networks, but actually you have, because a graph neural network is not that different from a convolutional neural network. And here is how you can write down convolutions utilizing the same compositional idea. So you begin with your data, you multiply that, by nothing, and that gets scaled by a certain quantity h0, but you then propagate your data through this time shift operator, okay? So in a sense, the only thing that has changed when you go from a graph to time, or actually the opposite, right? When you go from time to a graph, is that your shift operator, the operator that you are applying to propagate your information is different. In this case, it's a shift in time. And that's like a standard convolution. Now, if you have a standard convolution, you know how to build a standard convolutional neural network, right? So you do compositions of convolutions with pointwise nonlinearities, you stack this in layers, and that's the end of the story. So, that's all to say that maybe you don't know what a GNN is, and you don't know what a graph filter is, but actually you do. GNN is a CNN in which the convolutions are different. How are the convolutions different? Instead of using the time shift operator, we utilize the graph shift operator because the structure of the information is different. Now, this brings me to something that is pretty simple but not very well known, which is this idea of an algebraic convolution, okay? Which is that a convolutional filter, period, I'm not talking about time or graphs here, just a convolutional filter is a polynomial on some shift operator with coefficients hk, okay? And why do we do that? Well, because this is the same algebraic object, whether we are considering time graphs, but actually I'm not going to discuss that here, but if you consider a space for images or groups or graphons or manifolds, the latter two I will talk about them, then that definition of convolution stays unchanged. What is going to change is the operator that defines the convolution. Now, what is important about having this shared algebraic structure is that all of those convolutions have the same compositional structure, right? You're applying S over and over. That means that they all have some kind of equivariance with respect to the application of S, and it also means that they all admit some kind of pointwise frequency representation in, of course, the eigenvector basis of the shift operator. Now, by the way, I mean, this algebraic notation is, I found it to be very illuminating, particularly if you want to teach this. So I hope you don't get offended if I point you to my, to the website for my first year AI introduction class where we go through this, okay? And why? Well, because once you have understood this, you tell me, how do I build a CNN with multiple features? You just change the convolution to operate on matrices instead of operating on vectors. That's how you can build, but very importantly, it's still the same algebraic object. Now, once you have built these matrix convolutions, you stack them together, and that's a true CNN, right? Meaning the ones that we actually use in practice. There's no pooling or readout layers here, but this is a CNN with multiple features. So like the object that we actually utilize in image processing. Okay, now that's a graph convolution. Convolution. It's difficult to talk after lunch. This is a CNN with multiple features. A GNN with multiple features changes the convolutional layers into graph convolutions with multiple features. Good. Now, let me now go back to the main thread of the talk. This was like a small parenthesis to, help you maybe buy a little bit more into the merit of utilizing algebraic representations of convolutions. But the more important point that I want to highlight today is the following, which is that because we have this polynomial, all of these architectures admit a point-wise frequency representation. And again, this is something that you know, but let me explain it. And all of this is disarmingly simple, actually. So let me tell the story. So here we have our graph convolutional filter. It's built through recursive application of capital L. That's the Laplacian of the graph in this case. And I am going to consider the eigenvector decomposition of the graph. And instead of writing this composition on the node coordinates, I will write the composition on the eigenvector coordinates. Okay? And if you do that, you define u tildes, x tildes, z tildes. So you represent everything in this other coordinate basis. And what's going to happen now is that instead of multiplying by s, you will be multiplying by lambda, lambda being the eigenvalue matrix of the graph. And why is that relevant? Well, that is relevant because this eigenvalue matrix is diagonal. So you have transformed this complicated operation into a very simple one, which allows me to define this quantity, which has this name, which is the frequency response of a graph filter, which is the same polynomial, but with a scalar variable. Okay? And why do we define that? Well, because this relationship is pointwise, which means that the ith component of c tilde is given by h of lambda I acting on xi tilde. That's the ith component of the input. Good. There's a couple of observations here that I think are quite relevant for what I'm going to say before. The first one is that the frequency response is the same polynomial that defines the graph filter, meaning, again, same algebraic object, but it is on a scalar variable lambda. Second important observation is that this quantity here is independent of the graph. Okay? The graph, of course, does not disappear. The role of the graph is to determine the eigenvalues on which the response is instantiated. And this is maybe the first interesting thing that I have to say, because I'm going to utilize this later on to explain transferability of graph filters and to explain stability of graph filters, which is that the frequency response of the graph filter, it exists in isolation. It doesn't exist on a specific graph. It's kind of like an abstract quantity. It's that black curve over there. What the graph does is instantiating a specific set of eigenvalues. Lambda i's for the blue lambda i's for the blue graph, and the red lambda I hats for the red graph. And you can see how I can utilize this to do stability and transferability analysis, right? What I need to do is, well, somehow I need to be able to relate eigenvalues of different operators, and if I have relationships between eigenvalues of different operators, I can construct relationships between different filters. At the risk of overstaying my welcome, these are all things that you know. You just don't know them for graphs, but you know this for time, right? In time, this is the convolution represented in terms of shift operators. You are going to now project this into the eigenvector decomposition of the shift operator. The eigenvector decomposition of the shift operator is the Fourier series. Well, Fourier series, Fourier transform depends on the specific space on which you are working, but one of the Fourier. And the eigenvalues are the complex exponentials, okay? Which means that when you perform the same trick here, what you end up obtaining is a representation in terms of the Fourier series, or Fourier transform, whatever. I could do the same story. I mean, I'm not going to do it because this is not a talk about convolutions in time, right? But, once I point the connection with time, you should realize that the quantity that I am calling a frequency response is actually a C transform. And in this case, since I am talking about complex exponentials as eigenvalues, I should get the unit circle and unroll it, right? And, but the plot is largely the same. It's just that this will be a plot in the complex unit circle as opposed to a plot in the real line. And something that is very interesting, I think that most of you should know this, is that when we perturb time, high frequencies tend to be perturbed more, okay? Which means, which tells you something that for those of you that are old enough to have studied wavelets, which is that convolutional filters are unstable when we want them to process high frequencies. And we will see later on that the same problem arises in graphs. Okay, now that's the summary of this part of the talk, right? So I can, construct frequency representations of algebraic convolutions, which means that if you give me a filter defined by this operation, I can construct a polynomial, which is the same polynomial but on a scalar variable. And depending on the problem that you're studying, this S gets instantiated in different eigenvalues. If you're studying time, it gets instantiated on complex exponentials. If you're studying graphs, it gets instantiated on the eigenvalues of your Laplacian or adjacency matrix. If you're studying groups, well, I don't know how to explain that quickly, but if you're studying graphons, again, it will be on the eigenvalues of the graphon kernel. If you're studying manifolds, that thing will get instantiated in the eigenvalues of the manifolds Laplacian. Yes.
So in the previous plot, instead of having k going to infinity, you have like k finite.
Yeah.
You have like half of the plot, or how is that?
You mean in the time plot?
Yeah.
So this time plot is kind of is conceptual because I will need to do like a 3D plot in which I am showing you things in the complex plane so that it makes more sense to you. If you have k finite, the same ideas would apply. Yeah. It's like the reason why this. Let me answer your question specifically. So the same plot would hold if k is finite. But I just do want you to know that this is not the right plot. It's the plot that is closest to what I've been talking about without lying too much. Okay. Yeah. Good. But yeah, I think that I understand what you are trying to say here. I mean, like the thing is whether I am considering the whole unit circle or half of the unit circle. Is that your concern? No. Okay, well, we can talk about this later, Soledad. Thank you. Okay, good. So, I am done with the, I don't know, like what I would consider the basic part of the talk. I didn't say anything that is very difficult to understand, I think. At the end of the day, I am talking about polynomials, right? And actually, both of the polynomials I'm talking about are here in this slide. One of these polynomials, when we talk about graphs, is in the node domain. The other polynomial is in the spectral domain, is in the eigenvalues of the graph. Now, however, and very importantly, I have reduced the complexity of studying this object, which I don't know what this s to the power of k really is doing, into the complexity of studying this object, which is a polynomial, right? So I always run the risk of offending my audience when I go down to discussing polynomials on scalar variables because these are things we were doing when we were 10 years old, right? But the merit of this polynomial is not itself, but the fact that it allows us to investigate that more complicated object. Now let's put this to some use by talking about graphon filters and the transferability of graph filters. I am going back to time here, actually, images, to remind you of something that you know is true, which is that convolutional information processing, or convolutions in general, have limits, right? So, we would not process these different images with different CNNs. We would process all of them with the same CNN properly scaled. Why? Well, because the information that these images contain is all the same. That motivates the question of whether the same thing happens on graphs. This is a recommendation system. I give you a graph with 30 products, 50 products, a graph with 100 products, and then the question is, okay, if I now keep growing the number of products, is this approaching a limit or not? Well, the way to model this is to first consider a limit object of the graph. A limit object that is popular here is a graphon. And I can now ask the question, okay, so if I give you a sequence of graphs that converges to a graphon, do the graph filters and GNNs converge to corresponding limit operators? Well, to make a long story short, yes, they do, and we can verify that empirically. Okay, what I am doing here is I am training a GNN on a small graph and transferring that GNN to a larger graph. And you guys see that, I compare here the loss in performance that I would observe if I were to train on the proper size. And you see that this loss in performance is very close to 0. Which means that, it is true that these things approach some kind of limit object. The question is, why or how? Now, in order to do that, I'm sure that you know where the story is going, right? Why? Well, because I'm a one-trick pony here. I'm a eigenvalue kind of person, okay? So here we have our graph convolutions. They are polynomials on the graph shift operator, okay? A graphon, is kind of like a graph with continuous set of labels. It's a function in 0, 1 squared, okay? Which means that I can construct a kernel, which is, frankly, like a matrix multiplication here, if you allow me, the abuse of language, in which t acting on x is defined by this integral. And then I can go through the same chain of operations, right? I apply t once, twice, 3, whatever number of times you want, and that is a graphon convolution, which again, right, is algebraically the same object. If it is algebraically the same object, in the same way in which I got this architecture and I projected it into the eigenvector space, I can get this, and let me trace back. In the same way in which I got this architecture and I projected that into the eigenvector space so that I could end up with a diagonal representation on the eigenvalues of the graph, I can get this architecture and project it into the eigenfunctions of the graphon kernel and end up with a representation that is diagonal on the corresponding eigenvalues of the graphon. And I am using matrix here between quotations because, well, you guys know this is not truly a matrix because it extends, it is countable, by the way, but it extends to infinity. Okay? Good. Now that I have introduced these things, I can point to you something that should be obvious by now, which is that the graphon frequency response of a graphon filter is a scalar polynomial on variable lambda, okay? Which is, again, the same polynomial, right? This has to, I prepared this yesterday night, so if I get yesterday night, if it's getting repetitive, it's because it's still a fresh talk in my mind. But anyways, right, so we are again seeing the same polynomial. What is the difference now? Well, the difference now is that this polynomial is being evaluated on the eigenvalues of the graphon. Okay, and here I have the projections. Here I have the projection of my input signal on eigenfunction phi I, and here I have the projection of the output signal on eigenvalue phi I, and those two do not interact with other components. They get directly scaled by this quantity, which is precisely the definition of the graphon frequency response. And again, all of that, is the same derivation that I did before, literally the same derivation, because until you instantiate these things with numbers and you're operating with symbols on a piece of paper, the equations are identical. That's what algebra is, science of symbols, as I like to say. Okay, so again, right, so the frequency response is the same polynomial that defines the graphone filter, but on a scalar variable lambda. It is also independent of the graphone, and the role of the graphone is to determine the eigenvalues on which the response is instantiated. But here we have one additional step, which is that the response is also the same response of a graph filter, okay? And it is also, by the way, right, the same frequency response of standard time convolutions. And of course, this is true because these are all algebraically equivalent convolutions. Okay, how do we put this to use to understand transferability? Well, this is the instantiation of the graphone frequency response. Again, the frequency response exists in isolation. What happens when I particularize to a specific graphone is that this thing gets instantiated on some specific eigenvalues. The same filter can be instantiated on a sequence of graphs that converge to this graphone. And if I do that, now the frequency response on all of these graphs will be the same. And what will happen is that each specific graph in the sequence will be instantiating a different set of eigenvalues. Or to summarize, the spectral response of the graph and the graphone convolution are the same function, h of lambda. The graphone evaluates the response at the graphone eigenvalues. The graph, or the graph sequence, I should say, evaluates at the sequence of graph eigenvalues. And you should not be surprised to learn that the sequence of eigenvalues of the sequence of graphs converges to the eigenvalues of the graphone. And from that, you can prove convergence of graph filters to graphone filters. There is a restriction here, which is that h of lambda has to be Lipschitz, and I'm going to explain why that is necessary and actually very interesting in a minute. But before I do that, right, I have to emphasize that this band is universal. And actually, since I am requiring h of lambda to be Lipschitz, Lipschitz is a restriction on discriminability, right? So I am here giving you a universal warranty of transferability subject to a restriction on discriminability. Okay, so this bound here holds for all filters and graphones, as long as we have some minimal regularity conditions. And the reason for that is because, again, the analysis is on h of lambda. It has nothing to do with the specific graph or graphone. The only thing I need is that the eigenvalues of the the eigenvalues of the graph sequence converge to the eigenvalues of the graphone. As long as that is true, this theorem will hold. Now, I do have here a condition that is perhaps a little difficult to digest, which is that I am requiring the filter to be Lipschitz. Now, the reason why I need to require the filter to be Lipschitz is because eigenvalues of graphones accumulate around 0. Okay, so the graphone is a normalized kernel. Therefore, the eigenvalues are between +1 and -1. Actually, they're between -1 and +1. But when we get close to 0, convergence gets complicated by the fact that eigenvalues are difficult to discriminate from each other. All of the eigenvalues will converge to the respective eigenvalues, right? But there will always be an eigenvalue that is still far from convergence. If you require the filter to be Lipschitz, you preclude that from being a problem because, yeah, fine. I mean, these different eigenvalues, they may be converging to different places, but they are all going to be multiplied by the same h of lambda. Yeah, does that make sense, right? So all of these eigenvalues, I don't know which one is converging to which one because I am still not deep enough into the sequence of eigenvectors. Into the sequence of graphs. But it doesn't matter because they're all being multiplied by more or less the same quantity, okay? Now, this is also a little bit of a problem, if you wish, because it is telling you that the Lipschitz condition implies that convergence comes at the cost of spectral discriminability. And this analysis, or this bound here, this theorem, doesn't really tell you exactly how. To solve that problem, let me show you the results that we do call transferability of graph filters, which are not asymptotic, but finite n. Now, if you look at these finite n results, well, there's a lot of things that I would need to set up, a lot of quantities that I would need to introduce, but let me just tell you what are the fundamental two things that do appear, okay? This AH here, that's the Lipschitz constant of the frequency response, and this C is an arbitrary constant that we fix, which essentially says, I am not going to try and discriminate things whose eigenvalues are smaller than C. If that happens, then we end up having here a convergence which is of order 1 over n. And yes, this is telling me that because eigenvalues of the graph sequence are converging to eigenvalues of the graphon, the error that I make is related to the Lipschitz constant. So that's a very expected term to appear. The one that is maybe not so expected is this one, which has to do with the eigenvalues that we decide not to process. But if I explain things correctly, I mean, you already know why I need this restriction, which is that, I have this issue here with eigenvalues accumulating around 0. So those eigenvalues will be eventually, it's not eventually, they will always be some eigenvalues of the graphon that are impossible to discriminate when you give me a specific graph. Make sense? I hope it makes sense. Okay. Okay, so, and that's where you have your discriminability versus transferability trade-off, right? Because discriminating around lambda equals 0 requires a large Lipschitz constant so that I can discriminate those eigenvalues, but having a large Lipschitz constant increases the transferability bound, okay? Yes?
So the very last term is not 0.
Oh, yes.
And I expected, based on the convergence, that you would get to 0. Right. Now, if you don't get to 0, then how large is that error? Yeah. And how does that translate into what you said earlier, which we train on a small dimensional graph and we want it to work for bigger graphs? Yeah,
very good point. So the question is, this term here is not going to 0. That is correct. That's like a fixed error. C is an arbitrary constant that I can pick. Okay, so I can tell you can tell me, look, I mean, I want you to discriminate all eigenvalues up until 10 to the minus 3. So then C becomes 10 to the minus 3, and all of the other constants fall in place. Okay, the reason why you have convergence is because, I can now increase C and choose a larger n. Okay, so the difference between this theorem here and this theorem here is that this theorem is uniform for any C that you pick. In these other ones, convergence here is not uniform. It's uniform within the class of Lipschitz filters. Okay? Very good. And yes, the implication here is that there are things that you cannot transfer. Those things are associated with very small eigenvalues. Very small eigenvalues are the equivalent of high frequencies in images. So at some point, you're going to have very sharp borders that you're not going to be able to transfer, in a sense. Now, transferability is going from n to m, right? But of course, this is a triangle inequality, and this is the theorem that we call transferability. It has a 1 over n plus a 1 over m, and that's because just literally the triangle inequality. Now, the bottom line, or the end of the story, is what this figure here summarizes. So, you have the eigenvalue line, and there always is going to be some difference between the eigenvalues of the graphon and the eigenvalues of the graph. If you're looking at large eigenvalues, it takes a small n to approach that limit, and then you have transferability on the features of the data that are associated with these large eigenvalues. But then as you approach 0, then, if you want to discriminate two different eigenvalues, right? Like I want to discriminate this eigenvalue from this eigenvalue, well, I need to have like a very sharp filter, but this very sharp filter is very sensitive to the number of nodes that I need to approach convergence, okay? Therefore, and to repeat myself perhaps, yes, you do have the problem that some things you are never going to be able to transfer. Now, I promised a talk on neural networks, and I've been talking about filters for 30 minutes. I think I owe you a little bit of chat about graph neural networks. The reason why I have not been talking much about graph neural networks is because graph neural networks are compositions of filters with point-wise nonlinearities, right? The point-wise nonlinearities are point-wise. They have nothing to do with the graph or the graphome for that matter, okay? And for that reason, the convergence theorem or the transferability theorem that you can write down for graph neural networks is conceptually the same theorem that you would be able to write for graph filters. And again, right, I mean, the picture would be the same because the transferability bound is essentially the same except for a couple of constants there that are not very relevant. Now, I have to say something here that, goes outside of the mathematics. Everything that I've been saying, I can defend mathematically. There's something here that I cannot defend mathematically that much, but, empirically, I think that this is true, okay? Which is that the difference between a GNN and a graph filter is that the GNN has multiple layers. These nonlinearities are, in the signal processing parlance, the modulators, right? There's operations that reduce variability. Operations that reduce variability are going to get high-frequency components, and they're going to move them into higher frequencies, which means that as you encounter these features that are difficult to discriminate at lower frequencies, you can demodulate them into higher frequencies where you can discriminate them with a more transferable filter in a deeper layer. But I need to disclose and emphasize that this is just me talking. It's not the mathematics talking. Yeah.
Two questions. The first one is, what kind of nonlinearities can you tolerate? I assume that you at least need them to be Lipschitz.
Yes, they are Lipschitz nonlinearities, yes.
Okay. And the other one is, I did not expect that transferring to the case with nonlinearities would be straightforward. Mm-hmm. I anticipated that the nonlinearities would change all of the results about frequency response and kernels and everything you were talking about. Mm-hmm. Why they don't?
The nonlinearity, yeah, this is a genius move, and I can say that because it's not mine. I borrowed this from the scattering transforms papers of Malat. And the thing is this, I mean, the nonlinearity is point-wise. It's not acting on multiple components, right? So if you want to understand the transferability of that operation, the nonlinearity transfers perfectly. The only place where you can have lack of transferability is inside of the filters. You're applying that component by component, right? It's sigma of xi. So what does it matter that the graph changed? You're still applying the same nonlinearity. But that's a very good point because if I can make this parenthesis, I mean when I read this paper on scattering transform for the first time, half of the paper is talking with linear functions, and I was always wondering, I mean, how is this guy going to deal with the nonlinearity? And then he writes one line and says the nonlinearity doesn't matter essentially. And I say, yeah, of course it doesn't matter. But it's a very interesting point. Now, I've already showed you this plot here. This plot is on transferability. It's the same experiment that I showed you before, right? We go from a small graph into a larger graph, and we evaluate the loss in performance that we would observe if we were to train on the proper size. And you see that this quantity is going to zero. There's three things here that are being compared, actually. One of them is a graph filter, another one is a GNN, and another one is a GNN in which we enforce the Lipschitz condition. And this is to show that, it seems that the theorems can be validated in practice because the GNN is slightly more transferable than the filter. And furthermore, if we force the GNN to learn filters with a larger Lipschitz constant, the loss in performance is smaller. And I have also been throwing maybe a lot of information at you. So I thought that maybe we could take a brief break to talk about an actual application of transferability in practice. I am changing it to PowerPoint because there's videos here, and embedding videos in PDF is a challenge. let me talk about this idea of this concept of learnable perception, action, communication loops. The idea here is the following. So we are trying to use a graph neural network to navigate a multi-agent system. Okay, there's several robots here. They're trying to accomplish a task, and we try to coordinate them. We will do that with a graph filter, with a graph neural network, which is made up of graph filters. And the communication or the exchange of messages that is necessary to implement this graph filter can be implemented over the air. Okay, we don't need to have a central location doing the coordination of the robots. And because we want to deploy this in practice, we're going to use perception inputs that are being processed with a CNN, and the output of the GNN we are going to post-process with some action neural network. Now, the kind of problems on which we apply are something like this. So here, this is a campus, this is a map of Penn's campus. Here we have used semantic segmentation to annotate intersections, parks, and parking garages. And out of that, we construct this importance function, which is telling the robots, these are the important places where you need to go. And to define important places, we ask them to minimize the cost of the Voronoi tessellation quantization. Okay, and you can see here that as time progresses, the GNN is successfully navigating the agents to a place in which the loss is small. Now, but this talk is not about LPACs. This talk is about transferability. So then this is why I want to do transferability, because, okay, yeah, we can do experiments here. These are, 7 drones. They are being controlled by a graph neural network, so this is cool. But there are 7 drones, okay? So, you don't really need a PhD to solve a problem with 7 drones. This is one with 10 drones. Actually, my student Romina, who is somewhere here, and my student Fred, who is not here, will be annoyed at me. But yeah, okay. This is a lot of effort. It's a significant accomplishment. But this problem becomes interesting when you go from 10 to hundreds. Okay, when you go into a problem like this. Okay, and the thing is this. I mean, I am confident that we can experimentally. Why? Well, because in simulation this happens. I mean, we never trained on systems with 1,000 agents. But if we train on systems with 50 agents, we can transfer to 1,000 without any problem. Okay, so this transferability does manifest in practice. Okay, so and why? Well, because here there is information in high frequencies, by the way, because high frequencies in this context are essentially collisions. Okay, so yeah, you do have some high frequency components here that you want to avoid, but for the most part, most of the information that we need to process here doesn't really live in high frequencies. And and as I have shown through the theorems that I've been showcasing, we can transfer from medium size to larger scale sizes if we don't have these very high frequency components. Now that's a. Oh, give me a second, let me finish here, and then you can ask. That one was a plot. These are actual graphs, so you can see that actually the loss barely decreases as you scale towards 1,000 agents. Yes?
So you have like a cloud of robots, where is the graph coming from?
The graph is the communication graph between the robots, because I want to...
So as they change location,
the graph is changing, yes.
Okay.
Yes, but we train over that, right?
Nearest neighbor, what is this graph? Like K nearest neighbor?
Very good point. So I never explained what the graph was, so thank you for the question. Yes, the graph is a nearest neighbor graph. So each agent is connected to the 3 nearest neighbors. We do that because that's a more or less faithful representation of what an actual deployment would look like, because the challenge in wireless communications is not range but interference. So it's more or less reasonable to assume that you can communicate with 3 or 4 nearest neighbors. It's another very good point. What they are communicating are you remember when I introduced the diffusion sequence, which was constructed through multiplications by S? They are transmitting the outputs of those multiplications. Does that make sense? Good, thank you. And by the way, since this is really what's happening here, okay? So here, the robots are exchanging that. I mean, they're exchanging the output of those multiplications.
allow you to use the graph on there. So is that an issue, or is it something that
That's a fantastic point. Okay, so Soledad knows too much about this problem. So I am using 3 nearest neighbors. Graphons in the limit have infinite degree. Right? That's your concern. So yeah, there is a mismatch between these experiments and the theory. I like to interpret this as saying that the practical value of these results extends beyond the assumptions of the theorems. We can also construct theorems utilizing sparse graphons in which the degree grows logarithmically, and when we do that, we are approaching something that is close to these experiments. Good. Thank you for your questions. Let me go back to the main presentation and change directions a little bit. No, not this one. This one. Okay. So where are we? So far, I think I've done, or I hope to have accomplished the following. I told you that a graph filter is a polynomial on a matrix representation of the graph that is algebraically analogous to a time filter, in which instead of composing a matrix representation of the graph, we compose a time shift operation. I then constructed CNNs and GNNs by composing filters with point-wise nonlinearities and stacking things in layers. And from that, I moved on to study the spectral properties of graph filters. And those spectral properties, if you were not able to follow what I was saying, what you need to remember is this. They are the same spectral properties that you know for convolutions in time. And what I'm doing here is literally getting all of your basic signal processing and translating it to generic operators so that I can apply to graphs. I can not only apply to graphs, I can also apply to graphons. And when I apply to graphons, it allows me to understand the scalability properties of graph neural networks, or to be more precise, the transferability properties of graph neural networks from a medium-sized graph to a large-sized graph. And that is largely dependent on whether processing high frequencies is relevant to your application or not. Or to put it differently, it gives you a limit on how high the frequency components that you can process are or can be. These spectral analyses have other applications, and I want to utilize maybe 5 minutes to talk about stability and 5 minutes to talk about manifold neural networks. There's something that you will hear around when you talk about graph neural networks, which is that graph neural networks are permutation equivariant. That is elementary to prove, and they are. There is, however, one step that I don't really buy, which is that because of permutation equivariance, graph neural networks scale. And why? Well, because you can learn from this graph signal to process this other graph signal which you never have seen. And that has something to do with reality, but the truth is this, right? I mean, what you want is not symmetry, but quasi-symmetry. You want to be able to transfer from this graph to this other graph. And that's a different question. And to address this quasi-symmetry question, we do an analysis of stability to deformations. But look, I'm going to go through this quickly because otherwise you're going to start throwing tomatoes at me because you know exactly what I'm going to do, right? So graph unperturbed has eigenvalues lambda I. Perturbed graphs has eigenvalues lambda I hat. As long as these eigenvalues are not too different, the filter will be stable. But the challenge is this. I mean, it is not so easy to guarantee that the eigenvalues are close. And here you have an example. I'm doing like an epsilon perturbation of the graph, which is each edge I multiply by 1 plus epsilon. Like in my navigation experiment, I'm getting my robots, and I am scaling the environment by a negligible amount. When you do that, the eigenvalues move by 1 plus epsilon, which means that at low frequencies, nothing happens. But again, at high frequencies, your eigenvalues move a lot. And incidentally, again, this is also a phenomenon that happens in convolutions and neural networks. I mean, that's the reason why we need CNNs to process borders, for example. Anyway, so this is the figure, right? So when the eigenvalues are low, they move a little. High eigenvalues, they move a lot. Why is that a problem? Well, because at low frequencies, you can design your discriminable filters, and they will transfer, meaning you will leverage quasi-symmetries. At medium frequencies, you can sort of leverage quasi-symmetries, but at high frequencies, you cannot. Okay, it's impossible because you train your filter very carefully to train lambda h. Now I whisper at your graph, and you missed it completely. Of course, in practice, it would be impossible to train for these high-frequency components because you have both lambda h's and lambda h hats in your data, and you will never learn a filter that or a GNN that is able to discriminate these two features. What you need to do is you need to impose a condition, which we call integral Lipschitz, which is that lambda times h prime of lambda is bounded by a constant. That condition prevents the filter from changing at high frequencies. And look, I'm showing you pictures, but we do have theorems in our papers that actually work with Joan, which very happy to, and we did this very early on the project also. But anyway, so we can show stability here, and stability again gets controlled by the Lipschitz constant of the filters. Now that's application number 2 of frequency analysis. Application number 3 is on manifold neural networks. You asked me a few questions, René. Do you mind if I ask you a question? René, it's almost 2 p.m. We just had lunch. We're all tired. You're going to help me out, okay? Good. I hope I'm not annoying you. Am I annoying you? No? Okay. Okay. That wasn't very convincing, René, but that's okay. I will pay for this, I think. Yeah. Anyways, let's talk about manifold neural networks for a minute, okay? So these are standard time convolutions. What are standard time convolutions? They're polynomials on the time shift operator, okay? What is a graph convolution? Is a polynomial on the graph's Laplacian. Therefore, what is a manifold convolution? Okay, a time convolution is a polynomial on the time shift operator. A graph convolution is a polynomial on the graph Laplacian. Therefore, a manifold convolution is a polynomial on the manifold Laplacian. And yeah, that would work, alas, poor Jorik. Thank you, René, for putting it with me. Not quite. Because the Laplacian is a differential operator, right? So when you compose that, you end up with higher order derivatives. And by the way, that's a perfectly valid definition of a convolution, except not the one that we like to have. The one that we like to have is slightly different, which is that we would compose small exponentials of the manifold Laplacian, right? So we consider e to the minus capital T calligraphic L. Capital T is like a sampling time, and now we do have an operation that is diffusing information through the manifold, and this is now an operation that could be legitimately called a diffusion operation over the manifold. Actually, I should have asked this to Misha. He would have. Well, anyway, so Misha, we reutilize Misha's results quite a lot in this investigation. This is almost, because of course, right? I mean, what you want is to have the integral. That is the integral of h of t, e to the minus t calligraphic L, and that is what we call a manifold convolutional filter. Now, I am walking away, right? So you should call me here, okay? I'm kind of changing the game. But actually, I'm not really changing the game because let me remind you of what a continuous time convolutional filter is. It is the integral of h of t, x of s minus t, right? But x of s minus t, I can write it as this exponential. Okay, so a continuous time convolutional filter is an integral of the trajectory of the exponential of the derivative, in the same way in which a manifold convolutional filter is an integral of the trajectory of the exponential of the manifold's Laplacian. And why is that? Well, because these two things are algebraically equivalent. They are actually different homomorphisms of L1. This one is L1 exactly. The other one is L1 with a different homomorphism. Okay, good. Of course, I am going to construct spectral representations. And those spectral representations will be integrals of the trajectory of the scalar exponential function. That for manifolds. But in continuous time, it will also be the same integral of the same trajectory of the scalar exponential function. And by the way, I mean, when you look at that, you should see that these are Laplace transforms, right? Those Laplace transforms, in the case of a manifold filter, are instantiated on the spectrum of the specific manifold Laplacian, and in the case of time, they are instantiated on the spectrum of the derivative. The spectrum of the derivative is j omega, and if you put j omega over there, that's your Fourier transform, as you should have expected to happen. And yeah, you'll believe me now that I've moved into the frequency domain, that I can prove scalability of graph neural networks through manifold limits, and that I can prove stability of graph neural networks through manifold limits. Now, that's all I had to say. I have a couple minutes here for some concluding remarks. This is, I believe, the most important message that I have learned through my explorations of spectral properties of GNNs, which is this, that all convolutions and all convolutional neural network architectures share a common algebraic structure from which they inherit common properties. That is not an idle property to have. If you want to learn more about it, this is my website on graph neural networks, where this is explained in detail. I always like to do marketing for this class. I like it quite a lot. But more to the point, I did use this spectral analysis to investigate the transferability of graphon neural networks. And I told you that this is not as straightforward as you think it is, because you do have a problem with high frequency components, which you cannot discriminate with transferable filters. And I did prove that mathematically, and I have also showed to you that a very similar fact holds for stability properties of graph filters and GNNs. This is all. Thank you for listening, and if you have any further questions, I will be happy to try and answer them. Thanks.